Hi again, welcome back to you watching this video. So for this video, we're going to have another example in solving for the shear and moment diagram using the area method. So we have here a cantilever beam, and it is loaded by a uniformly varying load of 30 kilonewton meter. So the first thing that we need to do, of course, is to solve for the reaction. And we know that a cantilever beam has three reactions. We have the A vertical, we have the A horizontal, and we have the moment. Okay? So in doing so, let's start with our A vertical. So summation of forces vertical is equivalent to 0. All forces that are pointing upward should be positive. So we have here uh, A vertical minus the uniformly varying load of 30 kilonewton Newton meter times the span of 3 meters. And take note, since this is a triangular load, we multiply it by 0.5 because 30 times 3 is a rectangle, area of a rectangle. So to make it a triangle, multiply it by 0.5, and that is equivalent to 0. Okay, so 30 times 3 times 0.5, A vertical is equivalent to 45 kilonewton. Okay? Next, summation of forces horizontal is equivalent to 0. All forces that are towards right should be positive. For vertical or forces towards or pointing upward should be positive. Now for the horizontal, we only have one force, and that is A horizontal, and that is equivalent to 0. Now to solve for the moment, summation of moment at point A is equivalent to 0. All forces that are going to rotate clockwise should be positive. So what are those forces? So we have here an assumed direction of moment A to be counterclockwise. Therefore, moment A is equivalent to negative. Then we have here the uniformly varying load to rotate in a clockwise, so that is plus. So plus 30 times a base of 3 times 0.5 times the lever arm. We know that the resultant of a triangular load is acting 1/3 from the base. So the lever arm is equivalent to 2/3 of 3. Okay? So the lever arm is 2/3 of 3 is equivalent to 0. So this will cancel out. This will also cancel out. 30 times 3. Moment A is equivalent to 90 kilonewton meter. Okay? So we're now ready to draw our shear and moment diagram. So okay, this is A vertical, and that is equivalent to 45. Moment at A is equivalent to 90. Okay, so we can now draw our shear and moment diagram. Okay, so for shear, we will start at 0. We have a vertical reaction of 45. So from 0, we will go up by 45. So that is 45. Then we have here a uniformly varying load, and it is pointing downwards. So for shear, we have shear A is equivalent to A vertical, and that is 45. So shear AB. Shear AB is equivalent to 45 minus 30 times 3 times 0.5. 30 times 3 times 0.5. And that this is equivalent to 0. So from 45, it will go back to 0. Now the problem is, my curve can look like this, or my curve can look like this. There's another method that we can use in determining, no, by skipping the slope. But of course, the very preferable method would be the slope. Okay, but if you have this you have a problem like this, no, it would be best if we will be using the area method. Why did I say so na area? If you can observe, okay, you started from 45, your load here is increasing. From 0, it increased to 30. Okay? So, pag nag-i-increase yung load mo, of course, we expect that your area would also increase. But, if it is otherwise, from greater value to lower value, nagde-decrease, therefore, nagde-decrease din siya. Okay? So, since dito, our load is increasing, it is expected that my area would also be increasing. So, it would be concave downwards. Okay? Based on the area. Okay? So, let's verify. The derivative of shear with respect to x is equivalent to the load. What is the load here? 0. So the slope here is 0. So that is the slope. Now what is the slope here? The slope here is the load at this point. So that is 30. So more or less, this is 30 is to 1. Therefore, my first assumption is correct. So the behavior of the curve is concave downwards. Okay? So this is the point of tangency. Okay? Again, yung shortcut method, the load, mag-start ka dun sa point na yun. Is it increasing? Yes, it is increasing. Therefore, I can assume that my that my shear diagram here would also be increasing, kumakapal. Compared to this, from higher value to lower value, numinipis, it is getting slimmer, so it should also be getting slimmer. Okay? So this is my shear diagram. Okay, next we have here the moment diagram. So for the moment diagram, we have here a counterclockwise moment of 90 kilonewton. So that would go down. So 90, from 0 to 90. Okay? So, the next thing that we need to do is to determine the slope. Paano ba magiging behavior niyan? This is a first degree curve, second degree curve. So, it is expected that this would be a third degree curve. Okay? The derivative of moment. The derivative of moment with respect to x is equivalent to the shear at that point. And the shear at that point is 0. So, the slope is 0. Here, what is the slope here? It is positive 45. So, it is expected to go up. So, 45 is to 1. So, the behavior is concave downwards. So, that is the behavior of my shear moment diagram. So, this is my load. This is my diagram. Using the area or using the shortcut, the load here is decreasing. So from higher value to lower value. So the load here is from higher value and it is decreasing. Okay? So if there's any question, just comment down below and I'll try to answer them if I will be able to read them. Okay?